Hello, my name is Christopher Yamamoto, and this is my Physics 1 Lab 1. For Lab 1, we were tasked with observing the motion of an object moving at the same speed without changing direction. This object must come from a video that we recorded ourselves. Once we've captured this video, we were to analyze its motion and compare it to a computational predicted model that matches its motion. To analyze the video, tracker was used to extract the object's position at corresponding times, and to create the computational model, GlowScript was used to code a theoretical version of this motion. The main result of the lab was that an observed real-life model is not as perfect as a computational model. Models and fundamental principles. Newton's first law of motion, or inertia. An object at rest remains at rest, and an object in motion will remain in motion unless acted on by a force. In this lab, the object will follow this law as the object remains in motion throughout the entire video. Uniform motion. Uniform motion is a type of motion where the object moves in a straight line with constant velocity. In this lab, uniform motion will be presumed. A flat table was used as the surface of the motion. A cylindrical weight was then rolled across the table with its initial velocity coming from a push from my hand. A meter stick was included in the frame in order to calibrate the motion for tracker, and the object was to move across the distance of the meter stick in the video. And this was the video captured. This video was then put into Tracker, and using Tracker's tools, I was able to record the object's position every few frames to chart this data and create these three graphs. These graphs represent the object's x and y positions and the object's somewhat instantaneous velocity in the x direction. In order to make the computational model, some assumptions had to be made. The first assumption was that it's under ideal conditions, meaning there's no friction, wind, or an uneven surface angle to be computed into the code. The second assumption was that there was zero net force acting on the object. Any net force would mean acceleration, which was not the goal of the lab. As for the velocity that I used for the model was the average velocity of the object captured in the video, which was 0.331. The picture on the right shows the code used to create the computational model. This code creates a model of the movement and then computes it visually in graphs. Using the starter code provided in Lab 1 instructions, I set the initial velocity of the object to 0.331 meters per second, which was the average of the observed object. Then I set the velocity of the object to 0.331 meters per second as well. And as you can see here, these are the two graphs that GlowScript computed, representing the position versus time and the velocity versus time. As you can see, they both go to a little bit over 3 seconds, which was how long the other video was for observed. So, once we got the data from the observed object and the data from the computed object, I put it into Excel to create two cleaner graphs. The graph on the left, in blue, shows the observed data, which is slightly curved and imperfect, unfortunately. The graph on the right, in the red, is the computed graph, and it's perfect. Since we had to compare them, I put both of them into one graph to see the difference. As I said before, the blue line is a little curved. This curve begins a little lower than the orange computed line after the origin, but then it goes above the computed line before eventually meeting at the same spot in the end. As you could see from the graphs, they were not perfect, so there was some possible sources of error that could have caused this. First one is, since the camera was not set up on an object and was instead held in hand, the recording may not have provided a perfect environment for the tracker app to analyze the motion perfectly. Due to the hook on the end of the weight, the mass of the object is not perfectly uniform, which could have affected the motion. The setting was also not an ideal perfect setting, so there was probably some wind from the air conditioning. The table was not exactly 0.00 degrees flat, and the table and the weight were not perfectly smooth, which could cause some bumps. So what does it all mean? The results of this experiment tell me one main idea. This idea is that the motion of an observed object is not as perfect as the motion of a predicted computational model of that object. However, the computational model can display the motion of an object to a close but inaccurate degree. As seen on the graph, there is a close resemblance between the two motions. In conclusion, using computational models in imperfect environments will likely not give an exact replica of the motion in the real world, but if a rough estimate is needed, a correct computational model can be used. What if the x-axis was flipped? If the x-axis was flipped, as in the positive x and negative x switched, the displacement would be in the negative direction instead of the positive one. This would change the graphs to be flipped along the vertical axis, making it look like this. Thanks for watching.